So in this particular lecture, that is lecture number 3, we are planning, we will discuss about the different issues related to the complexity analysis of algorithms. And basically we will derive the running time of the algorithm with simple calculations. And also we would plot a graph and visualize the running time or the performance of the algorithm taking different input scenarios. We would also do best case analysis, worst case analysis, and also look into how can we do average case analysis of the algorithms, right? So that is all for this lecture, lecture number 3, okay? And in the previous 2 lectures, we have already seen that we have already seen these terminologies, right? Design of an algorithm and analysis of algorithm. So the design comes into picture when the input is known and the output is known. Okay, input is known and the output is known. So now we need to develop a transformation function, or we need to develop a function which transforms the input into the desired output space, right? So that is the concept of design. And this design so there might be different versions of the design, right, depending upon the quality of the output you require. So now we need to analyze the different designs which we come across. Or in simple words, I can say that different versions of algorithms which you design, they need to be analyzed, and their performance need to be discussed, right? It needs to be carefully looked into. And on the other hand, so how do we analyze the algorithms? So analysis of algorithms is possible through the a priori analysis, already said earlier in the earlier lecture, right? We have to do a priori analysis, that is the computing time, and also we can do using the profiling. So these are some of the concepts which we will see different algorithms in this particular lecture, and we will see different cases. And in this, another terminology with the algorithms is validation. So what is validation? Validation assures that the algorithm works correctly for all possible legal inputs without concerning its implementation in any programming language. So you will be having a set of valid inputs, again legal inputs, and after you have designed the algorithm, you need to feed these inputs and check whether your algorithm performs correctly or not, whether there is any issue in the process or in the algorithm that needs to be verified, right? So here we do validation. And the other important terminologies is that we have to do a priori analysis, right? We have to calculate the computing time without even executing, without even officially programming it, right? So we have to informally we have to analyze the algorithm. So that is the a priori analysis, and then proving that the algorithm produces the desired result and terminates. So this is also very, very important. And mathematical proof or verification techniques are open research problems in this particular case. And now, what is debugging? So debugging is also one terminology associated with the algorithms. So debugging happens means a posteriori, right? So after I have written the program, I have implemented the algorithm, then I need to do a posteriori verification. And in this case, okay, executing with the sample data sets to determine the faulty occurrences and to fix them up. So this is what okay, we have to debug. I think you are already aware. You have already gone through the introduction to programming course. So you already know what is the term called debugging. Right. So here we will see different types of computing time, right? Different types of computing time for one particular problem. So we'll just so the problem here is the problem of discussion here is that it is required to determine whether the given positive integer n is prime or not. Okay. So the problem here is given a number, okay, given a positive integer, my problem is to check whether the given number is prime or not. So now just start thinking, right? So start thinking that how can we, so this is a very simple problem. You might already have the solution. So now let us try to have the problem, let us try to design a very simplest algorithm to solve this problem. So the simplest algorithm is to simply divide the given positive integer from from 2 to, right, because 1 already divides, so from 2 to n minus 1. So this is the very simplest algorithm. Now let us formally write the algorithm here. So the version 1 is that to check the divisibility of n by k, right, divisibility of n by k for all k varying from 2 to n minus 1. So this is the very simplest algorithm. And now let us try to analyze the algorithm, this simplest algorithm. So now in terms of algorithmic notation, I can write the entire entire solution here as so I would start initializing. So let us take a variable called k is equal to 2. So now if n mod k is 0, right, if n mod k is 0 means this k, okay, which starts from 2, if it divides n and the remainder is 0, then n is not a prime and you have to terminate the algorithm. So if this is not true, that is the else condition. Else is you simply increment k equal to k plus 1, right, and then check if k is equal to n, then n is not prime, then n is prime, and you terminate it, right? Else what you do is that if this condition fails, then you continue, right? You continue incrementing the k value, right? So that is the algorithm here. And now now let us try to analyze this particular algorithm. We saw that if n is an even number, right, if n is an even number, then n mod k, okay, n mod k is executed once and only once. So if n is an even number, then n mod k is executed once and only once. So the earliest exit occurs when n is even number, okay. If the given positive integer which is supplied is an even number, then the earliest exit can be seen here. So which implies that the least or the minimum number of computations that take place when the exit is the earliest, right, is the earliest. So it is, so how can we quantify that one? So we will take for initialization, that is k equal to k equal to 2, we take 1 computing time plus 2 computing time for n mod k equal to 0, right? So n mod k equal to 0 to check this condition. So this is all, this is for the earliest exit. I'm talking about the computing time for the earliest exit of this algorithm. So 1 for initialization and 2 for the 2 for this modulus operator. So total computation time for exit, if the case is if n is an even number, right, if n is an even number, then the total computation time taken by this algorithm is 3, right? 3 is a constant. So now, so that this is the time complexity notation. You can see that I'm taking that as a t, right, a function t. So t of earliest is equal to t of best is equal to t of minimum is proportional to 3. That means the minimum time, the minimum execution time for this algorithm is proportional to 3. So what is 3? 3 is a constant number. We will see pictorially, we will see that how this constant plays an important role in the design of algorithms. So now let us move further. If n is a prime number, so in the previous case we saw that n is an even number, and now we take that n is a prime number. So the computations terminate only upon k equal to n. So in this case, this result is the latest exit time. So in the previous slide, we saw that the best exit time, and now in this we are seeing the latest exit time or the worst exit time we can see. So let us coin these words. T max is equal to T worst is equal to T latest is formulated as follows. So now let me try to calculate the time, okay, for the worst case exit. So in this case, k equal to 2 will be executed, n mod k equal to 0 will be executed, k equal to k plus 1 will be executed, k equal to n will be executed, and then continue. So let us take the time, that is the computing time for this particular operations is 1, this is 2, this is 2, this is 1, this is 1, right? And now I will also see what is the frequency of these calculations. So the frequency here, this initialization happens only one time, whereas n mod k happens n minus 2 time, because this is the repeating code right there. So n minus 2, n minus 2, n minus 2, and the continue will happen n minus 3 times. Now, as we had seen in the lecture 2, now we will simply multiply this time into frequency and then come up with the equation, right? So now let us see that how can we simply now multiply this time into frequency here. 1 into 1, 2 into n minus 1, plus 2 into n minus 2, 1 into n minus 2, 1 into n minus 3, and simply do simple calculation. So we'll see that this time, that is the worst time, that is the T worst or the T latest, T latest is proportional to 6n minus 12, right? This is 6n minus 12. Now, if you see this equation, 6n minus 2, what does it, what picture you get in your mind? That this is a straight line, right? This is a linear equation. This is a linear equation. And now I can say that T is proportional to 6 into n minus 2, and which is, if I neglect this constant term, then T is directly proportional to 6n, right? So the running time of the algorithm is linear. I can say that T is proportional to m. So T is equal to big O. Big O stands for the worst case analysis. So T worst is O of n, and the worst case analysis of this algorithm is a linear time. And we also saw previously that the best case execution was 3, right? The computation time was 3. So now let us plot a graph and see, analyze, right? Pictorially see what is the time complexity of this. So the best case in this algorithm which we have designed was 3, right? So let me take that this is a constant. This is the best case execution time of the algorithm. This is 3, and this which is also the T minimum. And now the T worst which I got was 6n minus 12, right? 6n minus 12. So 6n minus 12 comes here, and you get a very straight line here like this. Okay, so this gives a very beautiful graph, and now you can see that the best case and the worst case, they meet at a particular point, and this particular point is called the crossover point, right? And this particular point is called the crossover point. And we should remember that the time complexity of the algorithm can never be below this crossover point, right? It cannot be below this crossover point. The computing time, the best, okay, is between the best case and the worst case, and it is above the crossover point, right? It is above the crossover point, which we should remember here, right? So in terms of, I hope you got the idea here, right? So how to, just to make you, right? So you can see that this is the bound, right? This is the crossover point. So your computing time cannot come below this. It cannot go above this. So that is what is the idea which you can get from this one. So your computing time algorithm, the computing time of this algorithm will be within this particular time. And in this case, you will also means between this, right, between the T best and the T worst, right, you have the average time also. So we will see those how to calculate the average time in this particular lecture in the coming slides. Okay. So now in terms of order notation, so T best is equal to T lower bound, which is proportional to omega 1. So best case is notated, best case is represented by the big omega. So omega of 1 is a constant algorithm. So here it is proportional to 3. Simply we say that it is omega of 1. It is a constant time algorithm. And on the other hand, the T worst is equal to T upper bound, which is proportional to 6n minus 2 in this particular algorithm. So the worst case is represented as big O notation, and here it is O of n, right? O of n. So that was the time analysis with respect to the version 1, right? Now let us design a much more what we call efficient algorithm for this particular problem. So our problem was, once again, our problem was given a positive integer, right? We have to find n, that is n. We have to find whether that number is a prime or not. So in the version 1, what did we do is that we simply took that positive integer and we divided, okay, divided by k. So k went from 2 up to n minus 1, and that was our algorithm version 1. Now in this version 2, if n is a prime, then n is odd, right? If n is a prime number, then n is odd, right? We get the domain knowledge now. And if n is odd, then it is not divisible by, if n is odd, then it should not be divisible by k is equal to 2, 4, so on, 6, right? 8. Okay, so all this one. So it should not be divisible by even numbers. So this is the domain knowledge. Now can we modify this algorithm? Whatever the previous version 1 we had designed, let us now tweak it and modify that algorithm. So now what we do is that we would skip the even number division, right? Even number division. So the algorithm gets modified like this: k equal to 2. If n mod k is 0, then n is not a prime and terminate, right? So this, or else k equal to, I know I'm starting from 3 because I left 2 here. So k starts from 3 to n minus 1, but increment happens in step of 2, right? It happens in step of 2. That is very, very important here, right? Step of 2. So if n mod k, so the algorithms remains the same, only the new thing is that I am making an increment not by 1, I am making an increment by 2. So that is how it is saving my time. So if n mod k is 0, then n is not a prime, terminate, else continue, n is prime and terminate. So now let us try to analyze the time complexity of this algorithm. What is the best case exit? What is the worst case exit for this version 2 algorithm? So now in this particular case, right, in this particular case, the best case is equal to t lower bound, and which is equal to t minimum, which is equal to t earliest, is also same as 3, right? Is proportional to 3. So here the omega, it is big omega 3 in this particular case. So now let us take the other case. So the worst case, so k equal to 2, n mod k equal to 0. So it is 3 units of time, which we have already computed in the previous algorithm. Now in this particular case, right, the worst case would happen when the k would go from 3 to n minus 1 in steps of 2. So what is the computing time here? So the computing time here is k equal to k plus 2, and if k is greater than n minus 1, right? So this would happen, and this would take 3 units of time, and this 3 units of time, right? How many times this would be executed? This would be executed n minus 3 divided by 2 times. So now if on the other hand, if n mod k equal to 0, right, we have n mod k equal to 0, it takes 2 units of time, and how many times it is repeated? It is repeated n minus 3 divided by 2, right? So let us try to add this one and just get the worst case time complexity of this algorithm. So simply t worst is equal to 3 plus 3 into 3 into n minus 3 divided by 2 plus 2 into n minus 3 divided by 2, right? So now we get this particular. So t worst is equal to 2.5 n minus 4.5. right? So now just remember, just see what was the constant in the previous algorithm, and now you can see that this, though the order notation, the this n, both the time complexity, if you see, they are linear, but what has changed, the constant value has changed. This value is decreased in this particular algorithm. So in order notation, this remains the same. It is omega of 1 and O of n algorithm, like it is similar to the previous algorithm. So in this particular, so however, in the strict case, so T minimum is proportional to 3 and T max is proportional to 2.5 n. So in this particular algorithm. So now let us see the time complex. So T minimum for this algorithm is T minimum, right? T minimum is equal to 3, and this was in case of previous algorithm, right? So 6n minus 2 was in the previous, the version number 1 algorithm, and now, so we had the crossover point, and now you see the time complexity with the version 2. So with the version 2, you can see that 2.5 n minus 4.5. See, we see that the width of the time complex, that means the minimum, you can see that the worst case time has drastically reduced here. You can see that, right? The worst case time complexity of this particular algorithm, that is version number 2, has become almost less than half, right? So almost less than half, we can see from this graph, and that is how. And the crossover point for this particular algorithm will be here, and so always a good algorithm is one where the best case and worst case time complexity remains the same, right? So if they are in such a case, it is the best algorithm. But here in this case, the best case and worst case are not same, but they are almost very near. You can say that so this performs better, right? So here T max is equal to, in this particular algorithm, the version 2, T max is equal to almost half the T max of version 1. That is what the observation from this particular graph which we can make. Okay, so importance of constants, I think you might have noted down, right? So here this is the constant term here, 3, and here also you can see that this is also the constant term 4.5, right? So the crossover point changes. So as the constants change, the crossover point also changes, right? And also the important thing is that here 6 is the coefficient, okay, and here 2.5 is the coefficient in terms of the computing in this particular linear equation. So now we have observed the T best and the T worst. So can we define T average? So how will we calculate T average? So we know that the T average is between the best case and the worst case, right? It is between the best case and the worst case. So how will we calculate it? Okay, so T worst is equal to T max is called the upper bound, and T best is equal to T minimum is called the lower bound. And how to profile for average case practically? So practically, how can we do average case? So average case, maybe we can take different cases, like we have best case, we have the worst case, and in between the cases are average cases. So you take such input values, maybe 10 inputs or 100 inputs, and then calculate the time complexity of all the 100 occurrences, all the 100 inputs, and then you take the average. You divide by the number of times you did the experiment, you divide it. So that will give the average time complexity practically. So how to analyze for the average case theoretically, right? So this also we will see in for few algorithms in this particular lecture. So now, considering the same problem, which is detecting that whether the given positive integer is prime or not. So now the version 3, a much better algorithm can also be designed, right? So we also get the domain knowledge that if at all n is divisible, that is n is divisible it should be divisible by a number not exceeding n by 2. So in version 1, version 2, we went up to n minus 1, right? We went up to n minus 1. But by the domain knowledge, we can see, we can get to know that, right? We come to know that we need not go up to n minus 1. We can end up by, we can go up to n by 2. So now you can see that the time complexity of this version 3 algorithms becomes again half of this version 2, right? So it becomes almost half of this version 2 algorithm. And now can you combine the idea of version 2 with this one to obtain the worst case? So now this can be, this you have to do it, right? This you have to do it. What is the time complexity? And now a much more better algorithm, which is the version 4. Version 4 for finding a prime number is dividing n by k for k equal to 2 to root n. So previously in the version 3, I told that we can go up to n by 2, and n by 2 we can skip, right, the even numbers, right? We can skip those numbers which are even. And in this particular version number 4, the k goes up to root n. So root n is sufficient for us to find the prime. So now we have 4 versions of the same problem of finding the prime number, right, for a given positive integer. So version 1, we got the complexity C1n, C2n, C3n, C4 root n, right? So these are the complexity of the 4 version of the algorithms, right, for the same problem. So the interesting question would be that finding the relationship between C1, C2, C3 and C4. So all these things, right, the analysis part should be covered in your assignments. Okay, so whatever the problem you get, you must do such kind of analysis. Okay, you should plot the graph, you should do a priori analysis, a posterior analysis should be done in a very in a very detailed manner, right? So also you should represent the diagrammatically. So there are, related to this problem, there are some more questions here. So profile all versions to demonstrate upper bound, lower bound, and average computing time of this algorithm. And also the other problem, generate all prime numbers up to n. And okay, you have to analyze for every version of the algorithm you design, you have to analyze the time complexity, the best case, the worst case, the average case analysis should be done. Similarly, generate Fibonacci numbers, check whether a given number is a Fibonacci number or not. First is generating, then checking whether the number is a Fibonacci or not. So the next set of problems, algorithms we would analyze is the problem of computing p is equal to a power n. So p is equal to a power n. So the simplest algorithm for this one would be that, right, you multiply a, right, to get this answer, you multiply a how many times? To multiply a n times. So what is the time complexity of this algorithm in a very simplest, for the simplest approach is the O of n, right? It is O of n. So you have to repeat n multiplications, right? You have to repeat n multiplications, okay, for a, right? So now can we design, the question here is that can we design much more simplified algorithm, much better algorithm where the time complexity is less than O of n, right? Here the issue is to get the time complexity less than O of n. So now let us try to see version 1. So in case of version 1, which I already discussed, here p is equal to 1 and I take p is equal to 1, and for k equal to 1 to n, simply you multiply a n times, right? You simply multiply a n times. So p equal to p into a, you multiply, okay, n times, and this p into p star a is executed n times. So here the worst case, the time complexity t is proportional to n in this particular algorithm. So now can we design much better algorithm? I already asked this question. Yes, we can design it. So how can we design? So we see that there are some computations which are redundant, right? Which are redundant within this particular problem. So we can use that idea and generate a very efficient algorithm. So for example, if you want to calculate x power 16, So x power 16 can be broken down into x power 8 multiplied by x power 8, right? So this computations here, if you calculate x power 8 once, then that is sufficient. You can multiply it, you can multiply the answer and then you can get it. Similarly, x power 8 can be again divided into x power 4 into x power 4. X power 4 is again divided into x power 2 into x power 2, and x square is divided into x, like this. So now let us initialize this p value to x. So p equal to x, and p is equal to p into p. So this is the base form, right? So this is our base form. If p is equal to p into p, we have. So now how many times p is equal to p into p is executed, right? If n equal to 4, then number of loops is, if n equal to 4, then number of loops is 2. Then if n equal to 8, the number of loops is 3. N equal to 16, the number of loops, the number of times this p into p is repeated is 4. And n equal to 32, the number of loops is 5, right? So with this, can we generalize this one? Yes, we can generalize. So if 2 power 5 is equal to 32, then simply apply the log on both the sides, and then we see that 5 is proportional to log 32 here. Here you can see that t is proportional to log n. T is proportional to log n. So now log n, if we plot on the graph, log n is much better algorithm than, right? The log n algorithm is much better than O of n algorithm. So this algorithm is much efficient than the version 1. Let us now plot this, right? So this is O of n. This is the plot of O of n, and this is the plot of log n, right? So in this case, O of that is the worst case, and the best case remains the same. Okay, in this case, the best case and the worst case remains the same in this particular algorithm. If it remains same, then such an algorithm is called theta algorithm, theta of log n, right? So theta of log n algorithm. So in case where the best case as well as the worst case, they remain the same, though we tell such an algorithm as the theta of log n. But in this case, it is in this case the worst case is O of n, so it is not a theta algorithm, but I'm giving you the idea here. If the best case and the worst case of an algorithm remains the same, right? If it remains the same, then such an algorithm is the theta algorithm. So now in this particular problem, so we have taken that it is the a power is that a power n, where n is an even number, right? We have already taken that very simplest case. But what will happen when n is an odd number, right? Like x power 25, if you want to do, then simply you make one more pre-processing step, like x into x power 24. So now this becomes even, and now you have some pre-processing here, right? You with this whatever the answer you get for this one, you multiply with x1. So you have additional computing time here in this particular case, that is x, when the x power is, right, when the power is odd number. So in this case, the assignment questions would be that can you do profiling for average computing time for such algorithms? Carry out the strict sense theoretical a priori algorithm for both the versions, right? Version 1 and version 2. Right, so these two, we have discussed two algorithms, and we have analyzed the a priori analysis, right? We have computed the a priori computing time, and also we have plotted a beautiful graph, and we have seen that how the different versions of the algorithm play an important role in the design and analysis of algorithms. So the another problem, interesting problem here. This is the third problem we are discussing here. So in an array of n elements, right, we need to find out the number of distinct elements present without sorting the contents of the array, right? So you are given an array of elements containing n elements, and we need to find out how many distinct elements are there within that array, and we should not use any sorting algorithm for in order to do that. So what may be the case, right? how can we go ahead? So, okay. So the case one, we'll take some random case. So in this case one, we have given some numbers, right? 12, 15, 18, 16, 18, 18, 15, 12, 14, 16. So in this particular case one, the number of distinct elements are 5 here, right? If you go through this array, if you scan through the array carefully, then you will see that number of distinct element is 5, and the number and then those distinct elements are 12, 15, 18, 16, and 14. Let us take another example, case 2. So in this case 2, you can see that all the array elements are 12, and number of distinct elements is equal to 1. And which is the distinct element? The distinct element is 12. Now, can you observe from this one? Can you observe this one? The interesting thing here, this is an example of the best case for this particular algorithm, right? So this is the best case algorithm. We would see that how this can become the best case, but simply we will see that simply we will remember that if all the elements in the array are same, right, the same, then that is going to become the best case for this particular algorithm. Now let us take the case number 3. So in case of case number 3, we have certain elements, right? We have randomly put some elements, and here we see that number of distinct element is 2, and the distinct elements are 12 and 14, right? We also remember. So in case 4, I have given random numbers, but I see that all the number of distinct elements in this particular array are 10, right? That means, right, in this all the elements are distinct in this particular array. So what may be the case? This is the worst case, okay, input for this particular algorithm, okay, for this particular. Now we will design the algorithm, right? So will this algorithm exhibit best case computing time and the worst case computing time? Okay, so will this algorithm exhibit? So I have seen some case, I have shown some 4 cases, and I am telling you that this is the case, right? So now can you say that whether this algorithm, whatever algorithm you are designing here, will exhibit the best case computing time and the worst case computing time? The answer is yes, right? So then this is a good example to profile for average computing time, right? So this is also a good example for computing the average time, because you have the best case, you have the worst case on the other side, and in between you can take the inputs and then calculate the average time for this. So let us design the algorithm. Okay, so now we have the inputs, that is, let the input be A1, A2, A3, A4, A5, A6 up to AN, right? And now what we do is that we start. So your algorithm starts by pointing the first element, that is a distinct, let the distinct element be A1, that is the first element. Check whether AI is equal to distinct element for I equal to 1 to n. So you initialize the first element and then check whether the distinct element whether this particular next elements in the array belong to the same element, that is A1, right? The distinct element from 1 equal to. So this will give the one loop, right? So this will give the one pass for the entire array. So replace the content on the ith location if AI is equal to distinct element. So wherever you find, for example, here you find 11 and here you find 11, right? You have 11 here. Here you have 13, here you have 14, here you have 15. So first element was 11. So what you do is that you simply trace the element, and wherever you find this 11, simply you insert a blank here, right? You simply insert a blank here, right? So this becomes the blank, this becomes blank. So now, okay, they are blank. And algorithm terminates when all n locations become blank. So now in the next case, what will happen? 13, the pointer will get incremented, and this 13 will be the second distinct element. And suppose this is the 13, this is the distinct element, this is the 13 will be here. So what will happen is that this will also become blank, and this will also become blank, this will also become blank. So here there is a counter which stores the distinct elements 13 and 11 and 13 here. So here is an okay, this will be remembered that 11 and 13 are the distinct elements. Similarly 14, similarly 15, right? So the algorithm will terminate when all the elements are, the number of blanks inserted is equal to n. So if all elements are equal, then, so yeah, now let us take that case we have already seen, right? If all elements are equal, then there is only one distinct element and the blank counter becomes equal to n at the completion of the first cycle, right? So now I think you now will appreciate that particular case. So the best case would be that if all the elements are equal, right, same in the array, then you will make only one pass, one scan through the entire array, and all the element will be filled up with a blank space. So the best running time of the algorithm is proportional to one cycle, which is proportional to n, right? So t best is proportional to n. Now every cycle contains two parts, you remember now, right? So the first part is to locate the first non-blank location. The first part is to locate the first non-blank location. Non-blank location means the distinct element. To identify the distinct element, the second part is to continue the search from that point onwards to search the element equal to the distinct element and replace them by the blank. So that is the idea. So this is two parts. First is finding the unique element and then replacing the unique element, replacing the unique element, right, by a blank space. So that is the idea. So now let us see what will happen when all the elements in the array are distinct, right? So the case I told that the element containing all the distinct elements is the worst case, right? So hence time taken for every distinct element in one cycle through n locations, right, is one cycle through n locations. So t cycle, okay, is proportional to n. If all n elements are distinct, then the total time is proportional to n into t cycle, which is proportional to n square. So how many passes you need to do? Approximately you have to do n square passes, right? You have to do n square passes, okay? You have to do in order to find the worst case. So your pictorially, the best case and the worst case would look, for this algorithm, would look like this. So this is the best case, right? So this is the best case. This is the omega of n, and this is O of n square, right? This is the running time of this particular algorithm. And now how to profile the average case? So here we have the best case is proportional to n, gives the lower bound. T worst is proportional to n square, gives the upper bound, and T best, T worst, and okay, so T actual will be the T average, right? Will be less than less than T worst, and it would be greater than T best. So what will happen if the elements are in sorted? So this is also a question to think. Okay, what will happen if the elements are in the sorted sequence? Whether that will give the best case, and what if the elements are in the sorted sequence, all the elements are the distinct, and there are repeated elements. So all the different scenarios which you can think over it, right? So if you want to see some similar problems, you can go through the textbook of R.G. Drome and try to see the algorithm number 4.1 to 4.7, 6.1 to 6.6, 7.1 to 7.4. So you can solve these problems for getting additional knowledge, right? So another set of problem is to find the maximum element in an unsorted set of n elements. So finding the maximum element in a unsorted set of n elements. So you have an array, and now I need to find the maximum. So can you guess what is the best means what is the simplest algorithm for finding the maximum element? So simply what you do is that you initialize the first element, you assume that it is the biggest element, and then you simply scan through the element. If the element is greater than your whatever the first whatever your element is you have taken initialize, then simply swap it, and then you pass through the array and you will get the maximum element. So here is the algorithm, right? Formally we have written here max equal to a of 1. We have assumed that the first element is the max. Now simply for I equal to 1 to n, do If A of I is greater than max, then simply max becomes A of I. It means A of I becomes the max here. So in case of detailed analysis, A of I, right? A of I itself should be accounted for the consumption of 1 unit of time, because this is a fetch operation. I think in your computer organization and architecture, right, you already learned that A of I is the fetch location. So you can also take this into account while calculating the time complexity. So now in this case, let us do the time computing for this max equal to A of 1. Let us assume that this is a 2 unit of time, and for I equal to 1 to n, let us take that it takes 3 unit of time, and this, okay, this takes 3. So this is repeated for, okay, 3n for full cycle, right? This is 3n for full cycle. Similarly, if this is repeated, then this is 2n for full cycle, and 2 units if and if it is executed, right? So here, just to check, right? If this is the case, if you take 24, 20, 18, 16, 14, 13, 12, then in this particular case, we know that this is the maximum element, right? 24 is the maximum element in this particular array. So once the element is set, max equal to A of 1, right? Then what will happen is that max equal to A of I is never executed, right? In the set of algorithm. So what is this? So this is an example for the best case. This is an example for the best case. So the minimum time, the minimum exit time for this algorithm when the first element is a maximum element is proportional to 2 plus 3 into n. Simply as the calculations I have shown in the previous slide, you take it and just add it, you will get t is proportional to 5n plus 2, right? So this is a linear. Now that this is the best case, and now consider the worst case. So now let us assume that the maximum element is at the end, right? So no doubt, if your algorithm is very intelligent, if it can understand which is the maximum element and where is the minimum element, right? It can understand. Then simply you start, right? If you know that your array is sorted in ascending or descending order, you can simply start executing from the backside of the array, right? You can start from the n, and then you can simply make the best case for this one. But here, let us assume that we are not developing such an intelligent algorithm. We will start from the beginning, right? We'll start from our pointer will start from the beginning, and then it would see the worst case. And here in this particular case, every position there is a change of value, means change of max. So max is equal to A of I will be get executed, okay, as many elements are present here. So here in this case, T max is proportional to 2 plus 3n plus 2n plus 2n. So it is 7n plus 2. So in the previous case, it was T best was 5n plus 2. And in this case, it is 7n plus 2, right? 7n plus 2. So the time complexity, you can see that T minimum is proportional to 5n plus 2. T max is proportional to 7n plus 2, right? So this is the complexity graph of this particular algorithm. And now T average should be practically obtained in this case. So actual computing time is T is greater than T minimum and it is less than T max. So now in this case, if you take the order notation here, the T minimum will become omega of, this is the best case, it becomes the omega of n, and T max is the worst case, and it becomes the it is a big O of n in order notation. Now here we see that the order notation, since the order notation remains the same, omega of n is same as big O of n, then such computing time is called the theta n algorithm. So such a computing time algorithm is called the theta n. Okay, so this function is theta n. So there are different problems which you can try to solve, where you can analyze the best case, worst case, and average case. And here, like, you can perform union of two arrays and intersection of two arrays, ring sum of two sets, with sets having the elements in unsorted sequence. And how are the algorithms modified if the sets contain elements in a sorted sequence? So how will you modify your algorithm? So these are some of the questions to think over it. Okay, so another interesting problem, consider a set of n unsorted distinct elements. Check if an element called X is present in the set or not. So this is an example of searching an element, right? Searching an element in an unsorted array. So let us simply design a very basic algorithm. Let us assume that I is equal to 1, and continue. If ai is equal to x, then it is found, stop, else I equal to I plus 1, I is greater than n, then I is not, means then the element is not found, stop, else continue, right? So this exhibits the best case when the first element is the maximum, the first element, the element is present at the first position, right? This exhibits best case when the element which you are finding is located in the first location. So this is the best case. And the dominant operation here is ai equal to x is executed once and only once. So t best is proportional to 1, and it is a constant time algorithm. So now let us move forward. So this can exhibit the worst case when x is not present in the set, in which case ai equal to x, right? In which case ai equal to x is executed all n times and leading to the control to else. So here, if the element is not present, you simply, so you will start from beginning and you will end up the array, and you will see that the element is not there. In such a case, t worst is proportional to n, right? T worst is proportional to n. So in the, you can simply plot the t best is a constant, that is 1, and t worst is proportional to n. So the running time of the algorithm is in between t best and the t worst. So this is the running time of the algorithm. So you can also do detailed strict analysis and observe the differences in the exact time function. You can just go through. So now let us see how to, in this particular example, let us see how to calculate the average case computing time for searching problem, right? For the searching problem. So to theoretically estimate the average computing time, we shall list the following assumptions. The first assumption is the probability of a successful search is equal to P. So P is less than, so P is greater than 0 and less than, greater than or equal to 0 and less than or equal to 1. The probability that X can be located, okay, the probability of finding X at a particular position is denoted as P divided by N. And the probability that X is not present is 1 minus P. So now let us take the array, right? Let us take the array and just stick. So here, if you take an array, right? So the probability of finding a given element, right? Given element at this particular position, okay? So it is P by N, right? So how many positions are there here? So for all the elements, you must compute P by N. And how many locations are there where the element may not be found? So that is, this is n into 1 minus p, right? N into 1 minus p. So we will, in the next slide, we will try to do that. So the probability of finding the first element in the first position is 1 p by n plus 2 into p by n plus 3 into p by n plus so on, right? N into p by n plus the probability of not finding the element, right? Not finding the element is n into 1 minus p, okay, that is the at n locations. So now simply you will add it. So the t average will be proportional to n minus pn divided by 2 plus p by. So this is the theoretical time complexity analysis, but practically how can you do? You can take some cases, like you take 1,000, 100 or 50 cases. You can take, simply calculate the time, running time, and you take the average of, average means you divide the total computing time by n experiments. So that will give the practical average case analysis. So now we have discussed in this particular lecture the best case, the worst case, right, and some ideas related to the average case. So now the question to you is that which time factor is more important, right? When you design an algorithm, what is the most important factor, which is the best case, worst case, or average case, right? So now you can see that this through this graph, you can see that if this is the worst case running time of the algorithm, if this is the best case running time of the algorithm, and suppose this is the average case of the algorithm, now we can see that the most important is the t worst case, right? So usually what we do is that we usually, if we design in any algorithm, we usually calculate what is the worst case time complexity of the algorithm. So t worst case time complexity is very, very important for your algorithm, because that the worst case performance will actually check the stability of your algorithm, and according to the worst case time complexity, you have to fix the resources which are required for your particular algorithm, right? So that plays a very important role. And so if the resources are okay, if the time complexity, if the t worst is not computed, then that can be a problem, and that will make your algorithm fail. So analyzing it properly is very, very significant, right?